Alright, hi 11s, this is Mr. Lim here again, and this is our fifth video on intermolecular forces, and it's about dispersion forces, so let's get started. Right, so we're going to be learning about the source of intermolecular forces and how we can increase or decrease it within a particular example. Alright, so let's get going. Okay, right, so electrons are in constant random movement around the atoms in a molecule. Okay, so the electrons are not static, they're not stable, they're not like just not moving around, they're always moving in random motion around the molecule. Even the ones that are within a covalent bond, they are still moving, they are just more often going to be found between the two atoms. All right, so at certain points in time, they are unevenly distributed around the nuclei or around the nucleus. All right, so let's have a look at what that might mean. Okay, let's do H2. Okay, so H2 has two electrons. We'll draw one here and one here. Now, this is how you might show it in a Lewis diagram, but this is not actually how they exist. All right, so they might exist like this, with the two hydrogens there, and then one over here and one over here. They might also exist like this, where there is one over here and one over here. All right, and they might exist in a way where, one of them is here and one of them is here. All right, so they're all different orientations, arrangements of how these electrons can be found, right? And there's no reason why they can't be found here and here, all right? So these two electrons are always moving, they're moving randomly, and at certain points of time, they are unevenly distributed. So this would be a time where they are evenly distributed. This is probably a time where they're evenly distributed, but this is a time where they're unevenly distributed. There's more electrons on this side here, so this is maybe a more negative side, this is a more positive side. Over this point in time, they're more on this side of the molecule, so therefore this side becomes the negative side, this side becomes the positive side. And then here, they're more on this side, so therefore they make this side negative, they make this side positive. So this uneven distribution for an extremely short period of time, because remember, these electrons are moving very quickly, very randomly, so these particular arrangements all exist in, moments of time, right? But even for an instant of time, a dipole can be created, which effectively means a positive and a negative end of a molecule, and they exist for an extremely short period of time. So these are called temporary instantaneous dipoles. Temporary because, they don't last very long, and they're instantaneous, very, very short period of time, dipoles, okay, formed when these things are in those orientations. So the temporary instantaneous dipole, that's one of these things, of a molecule can induce, which means cause to occur, a temporary instantaneous dipole in a neighboring molecule, okay, because electrons repel each other, so then which can create an attraction between the two molecules. So the idea is that if I have two molecules here, okay, let's say they're two molecules of H2, okay, if these electrons are here, for this one, the electrons, even if they're over here and over here, because this is the negative side and this is the positive side for that instant in time, they're going to repel these electrons to move them that way, all right? And if they repel to move them that way, right, then the negative end of one, right, can be, when these electrons here move to this side here, they make this side the negative side and this side the positive side. And so this molecule here, which is that one there, this molecule here forced that electron's imbalance, and therefore forming a negative and a positive side, and for an instant can create a an attraction between the positive and the negative ends there. Okay, so the idea is that a temporary instantaneous dipole forces another temporary instantaneous dipole to form in a neighboring molecule, which then creates the attraction between the two molecules. So this attraction is called a dispersion force. Okay, and so it occurs when you've got, the electrons moving randomly, temporary instantaneous dipole forms, and then forces another instantaneous dipole, and then they attract for each other for a small period of time. Now, the key idea is that all substances, including other bonding types, including ionic, metallic, covalent network, they all have dispersion forces because they all have electrons that simply move around. But for some of them, it is the predominant type, mainly because they have no other type of bonding. Okay, so some substances, like ionic substances, will have ionic bonding and dispersion forces. But some substances only have dispersion forces. All right, so that means that the dispersion forces for them is the predominant one. Okay, so next, the dispersion forces that particles have with each other contributes to the amount of energy required to break apart in the form of melting or boiling. So in the last video, we went through the idea of, okay then, to have two water molecules here. Okay, so H2O, right? The bond between these two here is broken when you melt something or you boil it. Okay, the bond between those two is what is broken between melting and boiling. And this is a bond between two molecules. So this is an intermolecular force. And dispersion is just one type of those intermolecular forces. All right, so it is between the two molecules. So it is a intermolecular force, and it's generally weak, okay? And that is the bond that needs to be broken for something to melt or boil, okay? Now, another key idea is that the dispersion force can be increased by having more electrons within the molecule, okay? So what does that mean? Remember, if we have these electrons here just randomly moving around, if you have more of them, you might have, 5 or 6 electrons randomly distributed to one side, which would cause a much larger push on those electrons there, creating a much larger dispersion force, right? So the dispersion force can be increased by having more electrons in the molecule, creating a larger temporary instantaneous dipole, creating a stronger attraction. Okay? So then this is why hydrocarbons, which we learned about in the last topic, of increasing size, which means that if you get bigger, they're going to have a greater dispersion forces. Okay? Which is why short molecules of hydrocarbons are generally gases. Then they get longer, and then the bonds are stronger, which means at the same temperature, they're now in liquid form. All right, and then at even a higher size, the temporary instantaneous dipoles are even stronger, and then they keep them together and form a solid instead. All right, so something about solids, liquids, and gases is that you've got to remember it's about the strength of attraction between the two molecules. Okay, so if the strength of attraction is quite weak, right? So this is weak, and these are vibrating because, they've got energy at 25 degrees Celsius. This weak bond might be broken at 25 degrees Celsius, which would turn this into a gas, okay? But if I got two molecules with a stronger bond between them, right, even though they're at the same temperature, they're vibrating the same amount, so at 25 degrees Celsius. Let's call this one a medium strength one. Medium is not a very good word, but the idea is that it's just slightly stronger than the weak one, right? It's, only slightly broken. the idea is that that bond can break and reform and break and reform and break and reform. If it's done doing so, breaking and reforming at 25 degrees Celsius, it's going to be a liquid. Now, remembering that because they're all at the same temperature, the only thing that determines whether it's a gas or a liquid is the strength of these bonds. We have a weak bond or we have a medium-sized bond. If we have a large hydrocarbon molecule, the attraction between these two will be very strong. The temporary instantaneous dipole will be very strong. So even if it's going to be vibrating at the same temperature, at 25 degrees Celsius, this strong bond, or stronger bond at least, right, means it's not broken at 25 degrees Celsius, which means it can be a solid. Okay, so at the same temperature, the strength of the bond determines the state because it's holding it all together. Even though the particles have the same energy, the strength of the bond there holds them together or doesn't hold them together and determines its state, right? But if you're comparing stronger and weaker things, then they're going to have a higher melting boiling point as they get larger because the strength of those dispersion forces is larger. Okay, let's have a look at the last bit. The number of electrons, because remember we're talking about increasing the size, we're having more electrons, can be calculated by the identity of the atoms in the molecule. So effectively you could count how many protons there are and work out how many electrons, right? But if you just use the molar mass as a representation of the number of electrons, because generally as molar mass increases, the number of electrons increase, then you can just use that as a general idea and show that the molar mass, which is easy to calculate, right? The molar mass is proportional to the number of electrons and therefore proportional to the strength of the dispersion forces between them. All right. One thing you also need to remember about dispersion forces is that they are extremely variable, right? So some of these dispersion forces, if you've got a small molecule, you haven't got many electrons, they can be very weak. But if you've got lots and lots of electrons, they can be extremely strong as well. So what you've got to remember is that dispersion forces, they are variable strength. And a lot of people you'll hear is saying that dispersion forces are weak, but they're not. They have variable strength based on the number of electrons, okay? And so therefore, you need to take into account how many electrons before you can say that the dispersion force is weak, right? If it's got a very small amount of electrons, then you can say that the dispersion force is weak, but if it's larger, then you have to take that into account, okay? And that's it. Adios.